I'm Michał Piotrowski, and as it was said, I'm working at Erlang Solutions for more than 3 years already, and most of the time I'm doing MongooseIM and systems based on MongooseIM and XMPP. During my talk today, I will say about what Mongoose is, about motivations behind version 1.5, and the story about upcoming release 1.6. So, how many of you know about XMPP? Almost everyone. Okay. So, just for the record, XMPP is Extensible Messaging and Presence Protocol, which is used in message-oriented solutions. And MongooseIM is one of the XMPP servers. It is based on EJBRD, but the code base was heavily modified since we forked. And we are building XMPP solutions with MongooseIM in various domains, mainly in social media, gaming, and telecommunications. All these solutions are designed for high volume and scalability. And scalability is achieved mainly because of the Erlang VM and partially by the architecture of Mongoose and the XMPP itself. Mongoose is also a highly customizable platform thanks to the XMPP protocol and open source technology we use. The key target domains we already address are social media, gaming, and telecoms. The common part of these domains are messaging. It can be multi-user chats or one-to-one chats, but any of these domains are based on messaging, and that's why they use XMPP and MongooseIM. I also put here IoT, which stands for Internet of Things. It is smaller than the rest one. It may look like I put it here only because it's a buzzword, but not. We believe that our next main domain will be Internet of Things, where we can connect many machines or small devices together via XMPP and MongooseIM. And I hope this will be soon feature for Mongoose and next domains. The key features of MongooseIM is the horizontal linear cluster scalability. What I mean by that is that you can put more hardware to serve more users and to serve more traffic in your system. So it is always good to scale your software by adding more hardware or replacing hardware with some more powerful machines. Mongoose has configurable databases. The simplest configuration works with Mnisia only, but for more scalability, you can use MySQL, Postgres, or any other relational database which can be connected over ODBC layer. You can also use Redis for transient data like sessions or some other caches. It supports WebSockets, it has multi-user chat feature, and a lot of pluggable modules which implement certain XMPP extensions or can work with different authentication backends. And our Mongoose team thinks that there is no such thing like one size suits all. So that's why we are always open to build some custom extensions for our customers, because sometimes it may be beneficial to have something which is very custom for specific reasons, and we can customize Mongoose for customers' needs. Not so long ago, like half a year ago, we released the Mongoose version 1.5, and the motivation behind this version was meeting the challenges of modern mobile messaging with XMPP. We have a very good article about this on our wiki page. Here is the link. In April, we released some small bug fix release. And now I'm going to tell about the challenges for modern mobile messaging. The first one is stream management. In mobile networks, it happens very often that you lose your network connectivity. Either you go to a tunnel or elevator and your Wi-Fi disappears or your mobile network disappears. And during that time, some messages can be sent to your device, and you don't want to lose these messages. And you also may want to resume your previous session pretty quickly. And this issue is addressed by the XMPP extension called Stream Management, which Mongoose implements. Here is some small, simple sequence diagram describing how this may work. The next challenge for modern mobile messaging is complete engagement across devices. In systems with multi-login, you can have many devices connected to your account, and you want to have them in sync with each other. And this topic is addressed by another XMPP extension called Carbon Copies, with which if a message is sent to one of your devices, it can be copied by the server to all your other devices, which enabled the feature. It goes two-way. When you send a message to someone, it will be copied to all your other devices, and when someone sends a message to you, this message will also be copied to your other devices, which are online at the time when the message is sent. The third challenge for mobile messaging we said is the message history and synchronization. With mobile devices, you probably don't want to store the whole history on the device, and you want to sync your message archive when you come online after some longer period of time. And this is addressed by the XMPP called Message Archive Management. And currently, MongooseIM provides backends for archives in MySQL, Postgres, and other relational databases. And also, we have a backend for Apache Cassandra. We are going to support Riak 2.0 in the next release, and sometime later we will add the backend for DynamoDB. And that would be quick story about 1.5. And I think here's the most interesting part of the talk, which is the version 1.6, which will be released soon. And the motivation behind 1.6 are two. First is Devops Friendliness, and the other motivation is integration with Riak 2.0. What I mean by Devops Friendliness is the fact that there is no such thing like too much metrics, and to be able to observe your system correctly and to see what's going inside, you want to have many metrics exposed by your system. And in version 1.6, we changed the existing metrics backend from Folsom to Exometer, and we also put a lot of new metrics. Some examples are stanza size histograms, counting plain XML compressed and encrypted data size, so you can see how big stanzas are sent by your clients. And there are metrics for Erlang distributed network traffic, separate metrics for ODBC workers network traffic, and there is also a lot of module-specific metrics counting time operation of some specific actions like write or look up from message archive or roster get, roster set, and various other metrics. Why exometer? Before 1.6 we had our metrics based on Folsom, but we decided to change it to exometer. The first factor is better performance. Honestly, I didn't observe Folsom as a bottleneck in our system, but from previous talks this year, we heard that Folsom is not that performant, and also some of my colleagues observed that Folsom can be a bottleneck. But for Mongoose, the key factor to change from Folsom to exometer is the flexibility which exometer gives us. For example, it allows to create metrics calling a function when it's needed. So in Mongoose, we have an API function for getting the total number of active sessions, and we can define simply this metric in exometer in 2 lines actually, where we call the relevant function, and then we parse the output to fit into exometer internal data structures, which can be then reported to some external metrics services easily. And these are some examples of the metrics visualizations. Here we have the histogram and actually some percentiles of the MAM archive time, and here is the median size of plain XMPP stanza size of a system under load. The next motivation is the Riak to 0 integration. We already implemented the user-based backend in Riak, message archive, and private storage. And I'm going to describe in more detail the user and the message archive, how it was implemented. As you may know, in XMPP we have JITs, and JITs consists of 2 parts, which is username and host name of given user, and the host part is put into bucket. So every virtual host served by MongooseIM has its own buckets, and the username is the key inside the bucket. So we organize users that way, and any other data, for example, the creation time or some passwords or other data used to authentication, are put into Riak map. Thanks to this, you can use Yokozuna to search through your user base easily. Either to search for a given username or host name. And this was a relatively easy task comparing to the message archive management and its Riak backend. First approach was to organize the archive into weekly buckets, which makes the cleaning easier, because you can take the whole old bucket and remove all keys from this bucket. Also, archiving is easy because you are writing to specific backend. It is pretty straightforward. Every message is put into new objects. By objects, I mean that we write the same message for sender and receiver, so it is then later easier to read the archive. And in this approach, objects key contains local and remote JITs, and also timestamp of the message when it was sent. The value is simple term to binary, and the most difficult part of this approach is the reading, because in the worst case you need to fold over all possible buckets, weeks you already have. And to filter keys, in my first approach I used MapReduce key filtering to obtain relevant messages from the archive. And unfortunately it proved to have poor performance. pity I started the load testing after the implementation. I should have done it earlier. So I will probably not have to implement this approach. But when I started my load testing, I set up some scenario in which single user connect to the server, reads last 10 messages from the archive, and writes some messages to other user. The load testing tool I used is Amok. It is our own load testing tool, which we use widely to test XMPP installations. The tested environment was single MongooseIM node and Riak cluster consisting of 3 nodes. The goal was to connect 10K users sending 500 messages, which produces 1K objects in Riak. And I put some limit on the archive sync, which should be less than 30 seconds. The achieved result with the first approach was pretty poor. I was able to connect only 300 successful users, and the average archive lookup time was 60 seconds, which was not acceptable, and I had to optimize something. So I came up with the second approach when I organized the archive into buckets per user. So every registered user can have its own bucket in which all his messages are put. And this gives us less keys to filter. The archiving is still easy. It is simpler to read the archive because you don't have to fold over all weeks and all the weekly buckets. But it is harder to clean all the archive from every user bucket. The key and the object is the same as in the previous approach. And the achieved results were better than previously. I was able to connect around 1,000 users. The average archive lookup was less than 1 second, which was good, but only for first couple of hours. When we produced a significant amount of keys in every user bucket, we started to observe the same scenario as in the first approach. So the MapReduce key filtering started taking longer and longer. And the conclusion from my two first approaches is that MapReduce key filtering cannot be used to read the archive in real time. Here is the results. We can see that for the first like 8 hours, the MapReduce filtering was pretty fast, but after that it started growing and would grow infinitely if I didn't stop the test. So this is still not acceptable approach, and that's why I started to implementing archive based on Riak 2.0 search mechanism. I returned to weekly buckets and used Riak search to read the archive and query for specific time spans or filtering by owner and remote user. The key is the same as previously, but I had to change the object, and now in this approach it is Riak 2.0 map with 2 keys. One is message ID and the second is the message itself. And to search, I'm using 2 indexes. First one is the default index, which is Riak key. It is used to filter by the archive owner and also by the user with which we talk. And the second key is message ID, which contains the timestamp and the ID itself. With this approach, I finally achieved my goal, which was 10K connected users and 500 sent messages. The average archive time was around 150 milliseconds, and the 999 percentile archive time was 2 seconds, which I think is quite okay in big system. And the lookup time, by lookup time I mean searching keys and reading all the messages, was less than 3 seconds. Here we can see some graphs of the archive time and its percentiles. The lookup time, in worst case it was 3 seconds, but usually it was around one and a half. And the time to delivery, the message time to delivery from one user to the other user was 400 milliseconds, which is quite a big value, but maybe acceptable. During my implementations and the load tests, I discovered some limitations of the Yokozuna search mechanism and how it's done. I discovered that without indexing and the Yokozuna engine, I was able to write messages with average time between 5 and 6 milliseconds. But when I enabled Yokozuna, the average writing time was around 150 milliseconds. And you can see that the overhead put by indexing is very, very big. I didn't discover yet why we have such big overhead here, but probably there are some ways to optimize this. The second lesson I learned is to use Riak 211, where they optimize the write operation heavily, and these test results I show was done with Riak 211. With 204, the results were not acceptable. The next lesson I learned is to not put term to binary as the value to Riak map or any other Riak object which will be indexed by Yokozuna, because even if you set your schema and disable some fields with this binary data, it will break the indexing. I saw some crashes in Riak console complaining about the field with binary data about some UTF-8 formatting or something like that, and that's why I had to put the raw XML in the message field in the object. And this implementation is not done yet. I still have to make some optimizations, and probably I will try some other approaches without Yokozuna because of the big overhead it puts into the system. But so far the implementation is quite stable and will probably be merged soon into master branch. And that would be all from me. Any questions?
We've got time for plenty of questions.
Any thoughts on Riak versus, say, Cassandra? Or have you had a chance to even?
Not yet. I didn't compare Riak versus Cassandra.
Okay.
But such comparison would be interesting, definitely.
So Riak provides like 3 backends, right? Like memory, bit cache, level DB. Have you tried using different for different type of data as you have?
No, I didn't try it because you can set the whole Riak cluster to use only single engine. So I configured it to use LevelDB. But in my next tests, I will probably try Bitcask.
Yeah. Okay. In case of archiving is fine, but for the user base or private storage, as you
Mhm.
mentioned, I feel it's better to use Bitcask instead of LevelDB. Isn't so?
But you think it will be better to use Bitcask or?
Bitcask, yeah. Because
Okay,
we have only one key, right? We don't have any other indexes.
right.
So by default, we use LevelDB, is it? In the MongooseIM?
But
I'm not sure. I'm asking you.
yeah, I didn't try Bitcask yet, but I will definitely try it, and probably we will recommend to use Bitcask for some part of the data and LevelDB for others. But still, I have to do some more load tests and comparisons between uh, different engines.
Thanks.
Any more questions? I just got a general question. I mean, MongooseIM is a massively scalable messaging system, and I mean, with integration with Riak, how would you see the future development? What's on the roadmap? What's gonna come in the future days?
We currently have a roadmap for 1.6. We didn't define another versions yet, but as I mentioned, I think the IoT will be our next key domain, and we just started developing the XC extension of XMPP, which is efficient XML compression used in the IoT domain. So this will be probably part of the 1.7 release. And as of 1.6, Riak 2.0 integration and Devops Friendliness is the key features.
Right. Thanks very much for MongooseIM and React 2.0. Please thank our speaker for his talk.
Thank you.